Today I want to talk about for this TEAS preparation video. I want to talk about how we classify chemical reactions. Recall that a chemical reaction is any process in which at least one new substance is produced as a result of the process, the chemical change. You may have some reactants left over. You may have more than one substance produced. That's always a possibility. And we classify chemical reactions based upon significant features. But that doesn't preclude the fact that some chemical reactions can be classified in multiple categories. Now, the question arises, I hope, for you, is why bother? You know, what's to be gained from classifying chemical reactions? Well, if we recognize a chemical reaction as a certain type, we have an immediate understanding of a general concept of the process that's being described. For instance, for a combination reaction or a synthesis reaction, we're bringing two simple substances together, two or more, and making a more complex substance. All right, so we can subdivide these into major categories like this combination, decomposition, which is the opposite direction from combination, displacement or single replacement, double replacement reactions, or different types of oxidation reduction reactions. These are the major categories. There are subcategories also, and we mentioned a few of them down here under oxidation reduction. Combustion reactions, galvanic cell, which is a battery, an electrolytic cell, which is the process that we use to run a battery in reverse and plate out metals on surfaces. Think chromed bumpers. So the first one, a combination reaction or a synthesis reaction, is one in which a single product is produced from two or more reactants. So we represent that as a generic X plus Y equals XY. An example is calcium and sulfur. These are elements, solids, and a solid, and they produce another solid, but a completely different solid with a unique identity. All right, that's a combination reaction. If we run it in reverse, right? If we ran this reaction in reverse, go in that direction, then we could classify that as a decomposition. Where a complex substance, usually a compound, is decomposed and thus broken apart into simpler substances. Now, very often the simpler substances will be elements, but they don't have to be. They can just be less complicated. A single replacement reaction or a displacement reaction is one in which we have an element and a compound, and this element displaces one of these elements. Now, in our example, we take this as a metal and we insert it in this compound. Like that. This happens also to be an oxidation reduction reaction. And I haven't described what that is yet, but keep that in the back of your mind and we'll get to it again in just a few minutes. A double replacement reaction is where we have a compound reacting with a compound, and we swap partners. So if this C comes over here to B, this A comes over to D, that's an exchange reaction or a double replacement. And the example here is silver nitrate in solution reacts with sodium chloride in solution to produce silver chloride. In other words, silver replaces sodium and forms a compound with chlorine, and then sodium forms a compound with nitrate. These reactions are very often accompanied by precipitation. When we say precipitation, we're usually describing addition of two solutions together, which means everything is in solution, and then the reaction produces a solid. And over time, that solid will settle out, and you can see it collecting on the bottom of the beaker. Now, oxidation reduction reactions. In order to have an oxidation reduction reaction, there must be a transfer of electrons from one atom to another. If there are no transfers of electrons, then that is a non-redox reaction. Notice the short version of oxidation reduction is redox. It just sounds better if we put red first and ox afterwards. One of the clues, it's not always the case, but if you have an example where we have a single replacement reaction, where you have this, let's go back, where you have iron and copper sulfate. And the iron replaces the copper. Right? Actually, these are all solids. Whenever you have an element on one side of the arrow and it's in a compound on the other side, like that copper is in a compound here, or that iron is in a compound there, whenever that happens, it's always oxidation reduction. And I'm going to give you some rules in just a minute how to tell if you do have an oxidation reduction reaction, even if you don't have this scenario where you produce an element or you consume an element in the process. Now, oxidation is a chemical term that describes a reactant that loses electrons. So if this iron has lost electrons by combining and replacing that copper, it's lost electrons. Over here, it is neutral. It has a zero charge. In this compound, it has a 2+ charge, right? How did it get to a 2+? It went from a 0 to a 2+. We know it's a 2+ because sulfate is 2-. So how did it go from a 0 to a 2+? Well, you may recall, I've said before a number of times, you cannot touch the protons. The positive charges are off limits. And the only way that you can generate a charge in an atom is add electrons or subtract electrons. In this case, we've lost 2 electrons between this position and that position. That was a loss of 2 electrons. Okay? That's oxidation. Reduction is the flip side. We gain electrons. So this copper is also a 2 plus charge on this side. And when it goes from a 2 plus to a 0, right, it has gained 2 electrons. 2 electrons, 2 negatives will balance those 2 positives and make it neutral. That's reduction. Now these pairs, these oxidations and reductions always occur together. They are never separate, which means that this oxidation caused this reduction, and vice versa. This reduction caused this oxidation. And when they do that, when we say this oxidation here, this caused this reduction. This is a reducing agent. Right? And that means this would be the oxidizing agent. Because it's the one reduced. That's the way it goes. If it's oxidized, it's a reducing agent. If it's reduced, it's an oxidizing agent. Now, here's how you remember. This is a little mnemonic device. Oil rig, right? Oxidation is loss of electrons. Reduction is gain of electrons. A combustion reaction. Combustion reactions must have at least, combustion reactions always have elemental oxygen, O2. Always, always, always. Anything combined with oxygen in that scenario produces products, and this is a combustion reaction. Notice that oxygen is an element, and in the products, that element is found in compounds. So the combustion reaction is also an oxidation reduction reaction. And notice this is also a balanced equation. We learned how to do that in a previous video. Okay, what category would this one fall into? Notice we have a complicated compound, and it's broken apart into simpler compounds or elements, right? So this is a decomposition, right? Anything else combined with it? No, I don't think so. Not of the selections that we have available, right? Let's classify each one of these as either combination, decomposition, displacement, exchange, or combustion, right? Well, we do have a combustion down here because there's oxygen. We have magnesium element here. It's in a compound there. That's oxidation reduction. But it's also a single replacement. That magnesium replaces the hydrogen. So the hydrogen now is an elemental. So we've got a single replacement or a displacement and an oxidation reduction reaction. Well, we should have identified it also as an oxidation reduction. Oh, that wasn't one of our choices. My mistake. That wasn't given as a choice. Okay. So this one is a synthesis. We're taking two simpler compounds and making a more complex compound, or a combination reaction. It's also called a synthesis. And then we have a combustion reaction here. Okay. Now, suppose we don't have the that rule of thumb where you have an element on one side in a compound on the other, right? How do you tell if it's an oxidation reduction reaction? Well, we have a bookkeeping scheme. It's called the oxidation state or the oxidation number. And that is sometimes it is equal to the charge, but not always. Doesn't have to be. Like I said, it's a bookkeeping scheme to track electron movement. We need some rules, though. All right. So the first rule is every element, standalone element, if it's a single atom, if it's a diatomic element, if it's multiple atoms in the element form, the element, each atom is oxidation state 0. If it happens to be an ion, then the oxidation state on that monatomic ion is the charge on the atom. Oxidation numbers are assigned to the alkali metals according to the charge that they would acquire if they were combined in a compound. So the first column, or the alkali metals, are always +1. So that's lithium, sodium, potassium, rubidium, cesium, and francium. They're always +1. No matter where you find them, if they're in a compound, they are +1. Alkaline earths, next door neighbors, beryllium, magnesium, calcium, strontium, barium, and radium. Those are all +2. All right. Oxidation number for hydrogen is usually +1. That's if hydrogen is the first element in the compound, like this one. That would be a +1. So since this is a neutral compound, the chlorine is a -1. There are exceptions. If the hydrogen is combined with a metal, it will come second, and the metal will assume the positive charge, like aluminum hydride, and the hydrogen will be given a -1 charge. And that's fine, right? Hydrogen is just this proton, and then it has 1 electron. So this orbital, as the case is, can accommodate 1 more electron. So if we add an electron, we have an excess negative charge. Right? If we, however, lose an electron, now we have that 1 positive charge. Okay? So hydrogen can accommodate either one of those oxidation states, depending on the compound. Okay? Oxygen is usually -2 in any compound you find it, whether it's ionic compound or covalent. It will be -2 with one exception, peroxides. Right? If you have water, H2O, then that hydrogen is a +1 and oxygen is a 2-. But if you have a peroxide, like that, hydrogen peroxide, then this whole group is a -2. So that means each one of these oxygens is a -1. Now the halogens are a special case. If fluorine is in the compound, it's always -1. Never changes. Fluorine in a compound is always -1. Chlorine, bromine, and iodine are -1 when they're combined with a non-halogen. And that can be either an ionic compound or a covalent compound. It doesn't matter. So PCl3 means that chlorine is a -1, and phosphorus then would be +3 to balance the oxidation numbers. When we have a binary compound and we don't have elements that have been assigned values, Then we take the more electronegative element has the negative, acquires the negative charge. So for instance, if we have two halogens bound together, so we have chlorine and let's say iodine. So we have that compound. Chlorine is more electronegative, so it acquires the negative charge, and we say it's a -1, right? So that means a -4 total. That means that iodine must be a +4. Okay. Now, if we look, let me look on the periodic table. Now, that wasn't a good example. Let's say, let's make it 5. I'm trying to use a real compound example. There we go. That would be a real compound. For neutral compounds, the sum of all the oxidation numbers of every element in the compound must add up to 0. If, on the other hand, we have something like a polyatomic ion, like NH4 plus, right? That ammonium, well, let me write it over here, NH4 plus. All the oxidation states must add up to a +1. So hydrogen comes second in this case, so we're going to give it a +1. So this is a +1. That means +4 total, right? So nitrogen must be only 3 minuses, because a 3 minus and a 4 plus gives you 1 plus. Okay, let's see if we can do oxidation numbers for each one of these. Potassium dichromate. All right, we have rules, right? We have rules that will accommodate the oxygen and the potassium. Right? We have rules for those. So this is a total of 2 pluses. This is a total of -14. Okay? So chromium has to balance so that we get a neutral sum. That means these taken together, -12 total. So it means this chromium, excuse me, 2 chromiums. These 2 chromiums must supply +12 to balance that 12. So +12 here means each one of them must be a +6. So the oxidation number for chromium in this case is +6. All right. How about this polyatomic ion, carbonate, CO3 2 minus? We have a rule for oxygen, right? -2. So that's -6 total. And that means that this carbon must be +4 in order to add up, right, to a 2 minus. And we can follow the same procedure. Oxygen for manganese 4 oxide. Oxygen is 2 minus, so manganese must be a +4. PCl5. Chlorine is combined with phosphorus, and we have to assume that chlorine is a -1, so that means phosphorus must be a +5. Similarly, for sulfur tetrafluoride, fluorine is a -1, so sulfur must be a +4. Okay, so to decide if a reaction is a redox, we have to determine the oxidation states or the oxidation numbers for each of the elements and see if any of them change across the arrow. Okay, so let's look at this first one. There's zinc in an element, and there it is in a compound. So we know this one is a redox reaction. If we assign values to it, the zinc is a plus is a 0. The zinc in this one is a +2 because chlorine is a -1 each. Chlorine is a -1 here, oxygen's a +1, over here it's a 0. Okay, so we've identified the oxidation reduction, and since zinc goes positive, it loses electrons. It's oxidized. That means zinc is the reducing agent. All right, and hydrogen chloride or hydrochloric acid is the oxidizing agent. Specifically, the hydrogen contained in that molecule. How about the next one? Well, we determined already that potassium dichromate gives us a +6 for chromium, and that's a +6 chromium. None of the others change their oxidation state. This chromium over here, if we say 4 times 2 minus is 8 minus, and then we need a +6 from chromium to make the 2 minus total, then we got no change. So B is non-redox. Okay? The last one is a very special case. This yields this one, and let's see, this is, excuse me, that's aqueous. This is aqueous, and this is solid. Okay, so what's the oxidation state here? Well, it's -1 there, so this has to be a +1, correct? This one's -1, so this one has to be a +2, and that's a 0. All elements are 0. So if we go from, notice there are 2 of them here, 2 coppers. One of these coppers goes from here to here, and it's a loss of 1 electron per copper. And the other one goes this way, and this is a gain, 1 electron per copper. Okay, so notice that the total number of electrons lost in one process is equal to the total number gained in the other process. 1 here, 1 here. That's always the case. Every time you gain 1 electron, 2 electrons, 3 electrons, however many, you have to lose that many in the other process. Okay? So that means copper 1 chloride acts as both a reducing agent and an oxidizing agent. This is a special case of oxidation reduction reaction called disproportionation. Okay? So, those are all the main categories, and we don't have time enough to drill possible combinations, but at least you have an understanding of the overall classification of chemical reactions.